So let's assume that we have already performed our connected components labeling and we can address individual objects within a scene. The next step is usually to extract certain properties describing those objects. Now, we can typically either extract the boundaries of the objects, which then allows us to characterize precisely the shape of the object, or we can get some other properties that are effectively summaries of properties of the object shape, simply starting from the binary labeling of the pixels that belong to that object. So, for example, if one is trying to identify and label cells within a histopathology slide, you could extract representations of shape, and from those representations you get measurements of region size, region shape, which would allow you to accept certain regions or to reject others as being candidates of interest. And that can be applied to any sort of context. So let's have a look at the first context here, which is that we're doing this in the case of histology images. And so we are looking, for example, at identifying the interiors of cells which take a certain form. In fact, these are looking at cell nuclei. So we're looking at the nuclei of cells. You can see the cell boundary in the other images up here. So the cell boundaries sometimes can be quite faint. So this is identifying the cell nuclei. Once you've got the cell nuclei, you can then, first of all, you can localize where they are. So these yellow dots are localizing the centroids of nuclei. But you can also do other things like figure out whether the nucleus seems to be in the process of mitosis or cell division. And you can characterize internal structure of the cell depending on the type of staining that you've done. Now we can take another example that we have talked about in the lectures, where we have the rice grains on the desk. What we could have instead, and indeed this is in fact something that is done in food processing, you've got rice grains on a conveyor belt, and you've got a camera watching the conveyor belt, watching the rice grains rather, as they go past. And as the rice grains are, sort of fall off the belt, what you do is you arrange a series of air jets underneath. So it's an array of air jets underneath the belt. So as the rice grains fall off, they may be subjected to puffs of air that would kick them out of the main flow of the conveyor belt. So in doing so, you would get rid of certain rice grains from the flow into the hopper going into the next stage of processing. Now this is something that is, as I say, it's done in food processing, and the technology has existed for many years to do this sort of thing. What you might do, for example, is grab the rice grains from the camera, identify individual rice grains, figure out which kind of row they're in as they are moving down the conveyor belt. So where on the conveyor belt are they? And the conveyor belt itself you can think of as a two-dimensional field. It's moving in one direction, and you know the rate at which it's moving. But rice grains, as they pass, they're in a certain, let's say, horizontal position on the conveyor belt, and you can figure out where the rice grains are, and you've got this array of jets that match the horizontal locations. So let's say 100 jets, and the air jet just gives a puff as the rice grain, is falling over the edge. So you just need to be able to detect the rice grain as it passes a certain position, and everything else can be sort of hand-tuned to make sure that you deliver the puff of air at the right time to fling your rejected rice grains out of the manufacturing process. So to do that, you might want to say, okay, let's take rice grains that look like they're too small. So that would correspond to things like broken rice grains or fragments of rice grains. You could throw them away and then charge more for your bags of rice. So this is something that is typical in food manufacturing. Okay, so now I mentioned the use of sort of trying to characterize the boundaries of objects. So you can do that. The first step would be to extract the boundaries. And we're not going to spend a lot of time on this. It's not something that's examinable. But in essence, by choosing whether you use a 4-connected or 8-connected definition of neighborhood pixels, what you can do is you can define boundary pixels to be those that contain amongst the neighboring pixel contain one or more pixels that are 0 rather than 1. So you apply this test to all the pixels that have a value of 1, and that allows you to then, by looking for neighbors, either 4 or 8 connected, which are 0, you might label pixels that having such neighbors as being boundary pixels. Now that leads to some flaws. You can see there's some holes in here that have been labeled as boundaries, but that's the sort of thing you can correct with a few other morphological operations, which we'll consider in chapter 4. So depending on whether you choose 4 or 8 connected, you get a slightly different shape to the boundary, but there's a nifty way to make a description of boundary invariant to this, which we'll look at next. So once we've got our boundary description, pixels that lie on a boundary, one of the techniques we can use next is boundary signal encoding. So effectively, you start at one location on a boundary. So given that you've got boundary of a distinct region, a distinct component, you start at one of the boundary pixels. There's a way to figure out where to start, and there are ways to compensate for starting in different positions if, let's say, you rotate an object. So all of that can be handled. But let's say you start at one location on the boundary. You then track around the boundary, one boundary location at a time, and encode the spatial position of those boundary elements. And in particular, you can encode the spatial position relative to the center of the boundary. So that's a nifty technique that can be used. So I'm just going to very quickly illustrate that concept on our board scene. Okay, so let's have a look at how we go about doing this this sort of boundary representation description. So I'm going to make this easy, I'm going to draw my boundary as a continuous shape. And we're going to assume that we have some points that are defined along this boundary. Now, it doesn't actually matter where we start. We can just have a convention and start from that location. But relative to the centroid of the shape, which is, we'll look at how to compute the centroid or determine the centroid shortly. And bear in mind that we don't care about the interior. We've just got the boundary of the shape here. So this is shape boundary. So our aim now is to find some kind of description of this boundary, and we can make the description a signal that represents the x and y locations as a function of location along the boundary. So if we imagine that we index these points so we use a little variable k equals 0 for that point. This is k equals 1 for this point. This one here is little k is equal to 2, etc. So this is 3, 4, 5, 6. This is k equals 7. And so little k is equal to 7. We can continue going around this boundary and collect large k points, and the x and y coordinates of those large k points will be used as the signature. But there is, of course, that signature is, it characterizes the boundary. So this is the last point. That's going to be little k is equal to large k minus 1. So we have large k points. And we form the sequence x0, x1, x2. And in fact, it's a pair of sequences because that characterizes the x coordinates of the points. We can also have y coordinates, y0, y1, y2, etc. Okay, so this goes up to little x of large k minus 1, and this goes up to little x of large k minus 1. Sorry, little y of large k minus 1. Okay, so we've got a pair of what are called discrete signals. And these can be thought of as waveforms. So for example, if I had a very large number of points along here, a sufficiently large number, then effectively I could represent those points by a pair of curves. So if I can imagine that the curves would look something like this. Actually, that this would go negative actually. The way I've drawn this, that curve would go and stay negative for x. You may want to ask yourself the question of why that is, but it has to do with the way I've defined the coordinates. And I can also have a curve for y. So y starts off as positive and then goes negative. Okay, so so y also starts off as positive and then goes negative and comes back. Okay, so it may be something like this, perhaps not going back quite so high. Let's put something like that on there. So I've got a pair of points now, and this is just illustrative, okay? But the idea is that this is now, so it's we have x and also y displayed on this axis. So this pair of signals encodes the boundary shape, and of course these are discrete, so I've drawn these as continuous, but they're actually discrete points. The problem with this sort of encoding is that there are two problems. First of all, we've seen that if I use 4 connected or 8 connected, I get a different appearance to the boundary, right? There's a small difference in the appearance, and that difference in the appearance though can mean that comparing two shapes, when I've chosen a different type of boundary methods, so 4 connected versus 8 connected, means I'll get fine differences in the boundary shape. But the second problem, of course, is that if I imagine that I've started in a sort of an arbitrary location here on the boundary, and generally I can fix where I start, so I can make an algorithm that always starts, let's say, from the leftmost boundary point, or always starts from the rightmost boundary point. But if I rotate this shape, then that boundary signature will change. So one of the nifty things you can do is to take these two signals and encode them as a complex signal. So you would have z of k is equal to x of k plus j times y of k, where j is the square root of -1. So you make a complex signal, and once you've got a complex signal z of k, you can then take that into the discrete Fourier domain. And in the discrete Fourier domain, you can then look at the magnitude of the Fourier series of z of k. So this will be a Fourier series because z of k is actually periodic by this definition, since once I go around the large k number of points, I start back again. So it's a periodic signal that I've created here. So I can look at the Fourier series of that. And to remove the difference between, let's say, 4 connected and 8 connected, and I can use filtering to remove the high frequency components of the Fourier series. But also, if I were to rotate the shape around, the magnitude spectrum of that shape description in the Fourier space doesn't change because it effectively becomes a shift. And you may remember from, if you've studied Fourier transforms, that the magnitude of a Fourier spectrum is shift invariant, and so you would get that property naturally from this approach. So one thing to point out is that you may wish to, if you're not familiar with Fourier series, what I would recommend is having a look at the YouTube videos of a chap called Grant Sanderson. And why does this happen? Okay, I've got some stupid ad cropping up now. So, all right, I can't even skip the ad. So this is the Grant Sanderson page. It's called, his channel is called 3 Blue 1 Brown. I'll write that down here to avoid embarrassment with its cruddy YouTube ad system. I have a feeling that I might have grabbed the video as a link here. Let me just see if I've done something. No, I haven't. So let me grab this out of the video. Yeah, that's the right link. Okay, so right, so that's the link to that particular Fourier series video, but the series of or the channel is known as 3 Blue 1 Brown. And it's a chap called Grant Sanderson. Who's got, as I say, this excellent series of videos about mathematical topics. And in particular, his coverage of Fourier series is, well, his coverage of everything is really very good. It's really exceptional. So I do recommend, if you've not met Fourier series or Fourier transforms, and you are sort of worried about this, then please have a look at the Grant Sanderson videos on this. One further thing I shall say is that in the next chapter, when we get onto transforms, we're going to look at a very different approach to understanding two-dimensional Fourier transforms as a general linear operator. But you may want to have a look at the one-dimensional stuff first. But the way that we do it in the two-dimensional case, I think, is extremely intuitive and will give you hopefully lots of insights into how the Fourier series and Fourier transforms work, generally speaking. Okay, so let's now move on to looking at another type of signature. So when we talk about signatures in the case of binary region representation, what we're suggesting is that we're converting a shape or the binary region into some kind of bunch of, well, something like a hand signature, right? And it could even be something like a one-dimensional signal. And that's the role of projection signatures. So again, it's a way of summarizing the shape of an object. You lose information in doing this. There's no question about that. But sometimes the information you need is sufficiently well captured by this reduced representation that it's good enough. So for example, if you take the sum of binary pixels along parallel lines at one or multiple angles, then you can use that sum as a signature that can be quite useful. So let me give you a simple example of that, which comes from optical character recognition. But even before we get to optical character recognition, we can think about a situation in which excuse me, we want to characterize, let's say, well, that's actually the wrong scene. Let's go to our PowerPoint scene. There we go. So you may want to, let's say you've got this camera looking at a page on a desktop, and what you want to do is to now use that you've grabbed the page, but it's rotated, and what you want to do is to adjust the page rotation so that the page is in full alignment, like we show in D here. So a modern way to do this, slightly brain dead way, would be to train a neural network to do it, or train some kind of machine learning system to do it. But without training data, there's a really nice intuitive way you can do this. So what I'm showing here is the summation of pixels of pixel intensities along parallel lines. Okay, so basically I take one line and I sum the pixel intensities, along that line. Yeah, then I take another line, sum the pixel intensities, take another line, sum the pixel intensities. So this is one way to describe this is as projecting the image along one axis. So by doing that summation, then if I sum along these lines, then I get this kind of signature here, which has, it's because the lines, these summation lines are crossing the lines of writing, then I'm getting, I don't have very big peaks and troughs within that projection. If I rotate this slightly, if I rotate this to position B, let's say, so I've rotated this slightly, I guess I've gone that way, you can see that the distance between the peaks and the troughs of the projection signature has grown more well defined. And as I rotate 1 degree or so more, they get even better defined, and again they're super well defined. So by doing that, I can effectively figure out how to rotate my page so that my writing is nicely aligned with these summation directions. To illustrate that a bit better, imagine we take just this little chunk of text here. It was a dark and stormy night, and we do that summation thing. So imagine that where we meet pixels that are 1s, so we've got no pixels that are 0s along this line, we get a very large value in that summation. As we move further down, eventually our summation, so our lines, imaginary lines drawn through the image, begin to cut the letters that are dark. They hit them, and when we reach those points, the pixels there have lower values, so we get a drop in intensity. When we get to the tops of letters, you see that the intensity drops quite dramatically, because we have lots and lots of black along lines that sit within these two yellow regions, these two yellow dotted lines I've got here. And when we get to the baseline of the text, again we get a jump up to a peak, and then when we are beyond that, just between that yellow and the red, we may have the occasional bit of noise, but effectively we have high values in that summation again. And the point is that if these, so here the text is aligned, but if the text isn't aligned, then the effect you get is this. And as you play around with the alignment, you can figure out when your in and out letter contrast is very strong, and that corresponds to full alignment. So you can also use this to figure out, for example, what type of font you might be using. You can get a little bit of information about how things are typeset by using these signatures. So it's a really nifty technique, and you can relate the shape of the signature to these lines that are used in typesetting as shown here.